For Chapter 4, we'll look at moisture in the atmosphere. Here, first we'll look at the water reservoirs around the Earth. We'll find that most of the world's water is contained in the oceans. Of course, it's salt water. 3% over the continents. Of that 3%, 75% of it's tied up in the ice sheets over Greenland and Antarctica. 24% is in the groundwater, and then there's another 1% that we break out in the lower graph. Of that other 1%, 20% is in lakes, another 20% in rivers. The air has about 22% of that in the forms of water vapor and condensed water clouds, and also in the soil itself. This graph just looks at basic components of the hydrological cycle. How much evaporation comes off the oceans, leaving as water vapor, might condense into clouds over the oceans. You can also get evaporation over bodies of water over land. Also, you can get evaporation of the moist soil. You can get transpiration, which just means evaporation happening within plants, coming off the stomates of plants. Precipitation is obviously a sink for atmospheric water vapor, where you condense it into clouds and it might fall down as rain or snow or hail. Of that comes over to the land, you can get it stored in lakes, stored in aquifers and groundwater reservoirs. You can have the moisture increasing in the soil as it accumulates. You can go into plants, or you can run it off in streams and rivers back to the ocean. Here we're looking at the global water budget, and the numbers shown here are the percent of the average global precipitation. So we start with the oceans. About 84 units of water are evaporated, going into the overlying atmosphere. Over the oceans, you also get 77 of these units falling back as precipitation into the oceans themselves. The difference there goes into advection over the continents, again the horizontal movement of moisture, and that combines with moisture that was evaporated over the continents themselves to give them 23 units of precipitation over here. So since over the continents you have more precipitation falling than evaporation leaving the continents, you have an excess, and the excess runs back off to the oceans to complete the cycle. The most important points of this graph are that there's 5 times more evaporation over ocean than land. There's 3 times more precipitation over the ocean than land. That's based just because the surface area is mostly ocean of the globe. E minus P, the evaporation minus the precipitation, is greater than 0 over the ocean. They're losing more moisture by evaporation than they're gaining by precipitation. And the reverse is true over land, where they're gaining more water by precipitation than they are losing by evaporation. Again, the differences here is that the moisture advection moves that excess over the continents, and then runoff along the continents themselves run that 7 units back into the ocean by rivers. 70% of land precipitation is derived from land evaporation itself. Looking at the numbers here, how much of this comes from evaporation in the oceans? 16 over 23 is about 70% of the land precipitations derived from evaporation from the continent. 30% of land precipitation ends up running off from the ocean. So the 7 units divided by 23 units is the percent that runs back into the ocean. Moisture is a very important atmospheric property, and one way to measure it is vapor pressure, which is the force per unit area applied only by the water vapor molecules themselves. So you have an atmospheric pressure, which is the combined force of all the species in there, mostly molecular nitrogen, molecular oxygen. Vapor pressure just separates the component of pressure owed to water vapor itself. It's a measure of the absolute amount of water vapor in the air at a given atmospheric pressure. So for the United States, vapor pressure decreases as you move inland, away from the evaporative source of the oceans, and it especially decreases as you move into mountain lowlands because they're blocking moisture from coming into those areas. The symbol for vapor pressure is E. Vapor pressure is really hard to measure. It's hard to separate the pressure from the water vapor itself from the other species, so there's alternative methods to measure the absolute moisture content. One such method is the dew point temperature, which is also a measure of the absolute moisture content at a given pressure. One can calculate the vapor pressure from the dew point temperature, giving a table or a number of equations. Here you're looking just at how similar they are. They're really telling you the same information. Here's the vapor pressure distribution in January over the US, and here's the dew point distribution showing the exact same spatial distribution, so they're giving the same information. The dew point temperature specifically is the temperature that the air would have to cool to reach saturation at a given pressure. So the more moisture you have in that air, the less you have to cool it to force saturation. The dew point is always equal to or less than the air temperature, The difference between the two, the temperature minus the dew point, gives you the dew point depression. So the bigger the dew point depression, the drier the air is, or the further away it is from saturation. If the dew point and the temperature are the same, the air is considered saturated. So we have to understand what saturation is. Saturation really is when the rate of condensation, or water vapor molecules arriving on some liquid surface, is equal to the rate of molecules leaving that surface, otherwise known as evaporation. It turns out that warmer water has more energy, and so the molecules can more easily escape the liquid bonds when there's more energy in the system, defined by higher temperatures. Having lots of vapor in the air simply means there's more molecules that can stick to the liquid surface. As the air in the water warms, or the environmental system warms, more evaporation is occurring because there's more energy to break those liquid bonds and go into water vapor. So to have as much water arrive at the surface as is leaving now with increasing temperatures, you need to have more water vapor available to condense to the surface. So more vapor is required to achieve saturation as the air and water or the environmental temperatures warm. So saturation vapor pressure increases quickly with temperature as a result of that. Unfortunately, this has nothing to do with the warm air being less dense and having more room for vapor. That's a myth that I hope to dispel here. Here we're looking at 3 different scenarios. The first scenario is when the air is not saturated, when a drop's shrinking because there's more evaporation, having water molecules leave the surface than are coming back from condensation. The second example is considering saturation here, when there's equal amounts of water vapor leaving the molecule as are arriving at the surface of the drop, so the drop size would stay constant during saturation. And then there's actually supersaturation, which simply means there's more condensation, more water vapor molecules arriving, condensing into liquid water at the surface than are leaving the surface as evaporation. In this kind of environment, a drop will continue to grow. The rate of evaporation, again, is really related to the temperature of the droplets. You might consider if the droplets are small enough, they're about the same temperature as the environmental air, so the rate of evaporation increases with the environmental temperature. The rate of condensation, on the other hand, is really related to how much water vapor is just in the air available to arrive at the drops. This graph shows the relationship from something called the Clausius-Clapeyron relationship. As temperature increases to the right on the x-axis, the saturation vapor pressure, again, the vapor pressure required to have saturation, equal amounts of condensation as equal amounts of evaporation leaving a liquid drop, increases exponentially as the temperature increases. This table in the middle is just showing the same values in a table form. So saturation vapor pressure increases exponentially with increases in temperature. This graph, it's worth mentioning, is relative to a flat surface of fresh water. Now here are some of the complexities and why the saturation vapor pressure is more than just a simple function of temperature. The evaporation or sublimation rate off either ice or liquid is not just temperature dependent. It also depends upon other characteristics of the surface. The number of molecules escaping the particles also varies with these 3 things. The first is the phases involved. If you consider ice versus liquid, ice has stronger bonds, so it's hard for those molecules to escape the ice. So molecules can escape from liquid much more readily than from a solid ice. That means the saturation vapor pressure for ice are relatively lower even at the same environmental temperatures because it's harder to get those water vapor molecules to escape the ice lattice. The shape of the boundary is also important. The molecules can escape more readily from a highly curved drop or from an ice crystal, say the tip of a snowflake, than they could from a flat surface of water or a flat surface of ice. Saturation vapor pressures, therefore, for very small drops with high curvature are relatively higher. You'd have to have a lot of vapor pressure, a lot of vapor in the atmosphere to have equal amounts of condensation from a very curved small drop, which has high amounts of evaporation. The purity of the boundary itself is important too. Any kind of foreign substances that's dissolved in fresh water or in fresh ice diminishes the number of water molecules that are at the surface which could possibly escape. As a result, saturation vapor pressures for salt or dirty waters are lower than they are for fresh waters. To try to give you a sense of how this works, I'm showing some salt water here with dissolved sodium chloride in it, and they're replacing some of the water molecules at the boundary. Therefore, there's less water molecules unable to evaporate, so the evaporation rate will go down. As a result, you don't need as much vapor in the air to force saturation. Here's a flat surface of fresh water. There's plenty of water molecules to evaporate at the surface. They're all water molecules. And when you compare that with a curved surface, you'll find that this water molecule in the middle, the blue one, is surrounded by 4 water molecules, each of which are bonded to that water molecule, holding it back, whereas this curved one only has 3 water molecules holding it back. So the evaporation rate off this curved drop will be higher, therefore you need a higher saturation vapor pressure as a result. So increasing saturation vapor pressure would be seen going to the right here, even at a constant temperature. So if you add contaminants to water, cloud condensation nuclei for example, you can lower the saturation vapor pressure. You don't need as much vapor to force saturation. If instead you have very curved, very small drops, you would need a whole lot of water vapor to force saturation. Relative humidity is a measure of how much vapor is actually in the air at one time, in other words, the vapor pressure E, relative to the amount of vapor that's required to reach saturation. So it's just the ratio of how much vapor you have, the vapor pressure, to the saturation vapor pressure expressed as a percent. So you can change relative humidity either by changing the amount of moisture in the air, changing the vapor pressure, or by changing the temperature in the air, which changes the saturation vapor pressure. This graph's just showing a constant amount of moisture, where the dew point temperature is constant over time over the course of a day. However, during the day, it increases temperature. Temperature is shown as the blue line here, and when temperature increases, the saturation vapor pressure increases, which means the denominator gets bigger, and the relative humidity, therefore, has to decrease. When the temperatures drop, so does the saturation vapor pressure, and the relative humidities rise. Another example thinking about this is using my bucket example. Let's say this bucket represents 50% relative humidity. In other words, it's 50% full of water. If we want to increase the relative humidity here, we could either increase the amount of water in the bucket by adding, say, moisture, or we can alternatively decrease the size of the bucket, how much it could potentially contain. Should the bucket actually become full, the relative humidity equals 100%, we consider it saturated, and any extra water vapor is therefore forced to condense into liquid water drops. Other properties of water to consider: water is really unique. It occurs at a solid, liquid, and gas in natural environmental conditions. That's the only gas we have on Earth that does that. It has a high specific heat capacity, which we talked about in past lectures. It also has high latent heat amounts, and we can look at that with a graph. This graph shows how latent heat works in the atmosphere. If you evaporate a liquid, you're removing heat from the system in order to change that liquid to a more excitable gas. You have a sense of this by getting out of the ocean or out of Boulder Creek. Anytime evaporation occurs, you cool down, you're losing heat. It goes the other way if you condense vapor into clouds. You actually release that heat back to the environmental system. You can also consider freezing. If you take a liquid and freeze it into a solid, that's a less energetic state, so therefore it gives off heat as the excess energy. You could, of course, melt solid and go into a liquid, and therefore that takes heat to do that, so you're removing heat in that system. Also, you can go straight from a solid to a gas in a process called sublimation, and that also removes quite a bit of heat, more so than evaporation does. Or you could take gas and deposit it back as a solid. So for example, frost on your car windows in the winter is an example of this, where the vapor never went to a liquid, it went straight from gas to a solid, and that actually adds heat to the surrounding atmosphere. Evaporation again removes heat, takes energy to go from that sluggish liquid to an active gas, so it removes heat from the system in that process. Therefore, the water vapor itself is carrying that source of heat. So in order to get the heat back out of it, you simply have to condense or freeze it out to get the heat back in the system. An example of how this works in the atmosphere: the trade winds, which are strong winds at the surface over the subtropics, constantly blow over the subtropical ocean, forcing evaporation. That cools the subtropical area from that process, and then the water vapor moves over, say, the mid-latitudes in the Boulder area, condenses into clouds, and that adds the heat to that system. So overall, the whole process was moving heat from the equatorial regions to the mid-latitudes by latent heat exchange. Latent heat transport accounts for about half of poleward heat transport by the atmosphere and about half of the vertical heat transport. So the movement of water vapor upwards condensing in the clouds is the vertical component, or the movement of water vapor from, say, the subtropics towards the polar regions condensing in the clouds is a meridional or poleward heat transport. So what are clouds? Well, they're liquid water droplets, or they're ice particles, or some combination of both of those things. They're not water vapor. Water vapor is invisible. When water vapor condenses into liquid, we can see them as clouds, or when water vapor deposits into ice crystals, we can see them as clouds. For a cloud to form, obviously you need to have some moisture. You also need to have condensation nuclei. Now the condensation nuclei part, they are needed to form a cloud in general, and there's a few reasons that this is why I brought about the complexities of saturation vapor pressure. The first thing you consider is a relatively large aerosol where water vapor is condensing on it. As it condenses and forms immediately a larger drop, you get past the curvature part, so it's easier to get saturation on a larger drop than a smaller drop. So if they form on a large particle in the first place, they have a better chance to continue growing. You get past that small curvature part I mentioned about. Also, you can consider adding very small aerosols to a droplet, which increases the solutes in there, again decreasing the saturation vapor pressure, making it easier to force saturation or to grow that water drop larger. The truth is, you need condensation nuclei in the atmosphere to lower the saturation vapor pressure relative to those drops so they can continue to grow. Globally, it's a heck of a lot easier to grow clouds with condensation nuclei than without. There's two types of condensation nuclei, your typical condensation nuclei, and then you have an ice nuclei as well. Ice nuclei are much harder to find. They actually mimic the ice lattice, so ice is more likely to deposit on those surfaces mimicking that lattice. The best ice nuclei is actually another piece of ice, so it becomes exponential processes in clouds. When you get some ice particles, it's easier to grow ice upon them. The third thing you really need is a means of cooling the water vapor to cool it to its dew point to force initial saturation. Now it turns out when you push an air parcel up, it is forced to expand. In other words, does work on the environment as it goes up because it's encountering lower and lower pressures as it goes up. It expands. That expansion forces cooling. Again, it's really doing work on the environment. In order to do that work, it's losing energy and it's cooling. As a parcel goes down in the atmosphere, it gets compressed by increased pressure, so the atmosphere is doing work on it, which adds heat, kinetic energy, to that parcel, increasing its temperature. So rising parcels will tend to expand and cool, and sinking parcels tend to compress and warm. Since rising air cools, anything that lifts moist air upwards can possibly force saturation by having it cool to its dew point. Here's just 4 scenarios of how you might lift air up in the atmosphere. You might get convection, where the warm surface air becomes unstable and buoyant and wants to rise. As it rises, it expands and cools and forces a cloud if there's enough moisture. The second one is orographic. As moisture gets pushed and forced over a mountain, it goes up the mountain, cools, might reach its dew point for saturation. You could also have fronts do the same kind of thing, where you have a cold front advancing here, cold air advancing into warm air. Cold air is more dense than warm air, so it wedges underneath, forcing the warm, moist air up, possibly forcing saturation. You could also have convergence, which means airflow is coming together at the surface. Since it can't go down to the surface because it's a solid surface, it has to go up. Again, air that goes up cools, could force saturation. What's left out from these diagrams are other mechanisms like fog mechanisms. If you have a moist, warm air mass that moves over a cold ocean current or a cold continent, that might cool that air mass enough to force saturation, forming low-level fogs. Here's a global map of January precipitation. You can see a lot of the world's precipitation happens along what's called the intertropical convergence zone. This is an area where the trade winds to the north are coming from the northeast, the trade winds south of the equator are coming from the southeast, and so they converge at the surface, forcing uplift. Rising air cools, forcing clouds. Other places in January that get a lot of precipitation, the Pacific Northwest. Here it's really a function of cool, moist air arriving over the Cascade Mountains, orographic uplift, but there's also a number of active fronts in this area that also force uplift as well. Over this area, it's mostly frontal precipitation, meaning cold and warm air masses colliding, forcing the warm air mass up and over and forcing it to condense. This is showing a cross-section across California, just showing how strong the orographic effect is. Moisture streaming in from the Pacific Ocean from the west here, hitting Sacramento with a certain amount of precipitation. As you go up and force orographic precipitation, you're getting higher and higher amounts of precipitation on the windward side of those mountains, leaving less water vapor available for the atmosphere on the other side. At the same time, dynamically, air comes down and compresses and warms, also dynamically reducing the amount of rainfall in what's called the rain shadow region on the leeward side of the mountain. Boulder is in a similar position, just further inland overall. Here's another map just of global average precipitation. Here's the ITCZ, that convergence zone that happens along the tropics. You also get hot plates, so to speak, over these warm continents. They cause convection in that converging air, so you kind of get a double whammy effect of convection plus convergence along the intertropical convergence zone, causing extreme rainfall rates around Indonesia, the Congo Basin, and parts of the Amazon as well. You can clearly see some rain shadow areas like Death Valley here and interior deserts in the US Southwest. They're simply blocking the moisture from those mountains, or you can consider those mountains wringing out moisture by rainfall before that air drops into these lowland valleys. Here's an oceanic desert, and this is a dynamic effect by having a cold ocean current that suppresses convection and limits the amount of storms that can possibly occur here. The key points for this chapter are that the dew point temperature describes water vapor amounts at a given atmospheric pressure. Saturation in air means that there is as many water vapor molecules arriving on a liquid or ice surface as are leaving said surface. Relative humidity quantifies the degree of saturation of the air, and it's a ratio of how much moisture you actually have versus how much you could potentially hold at a given temperature. The latent heat of water is an important means of heat transport in the climate system, and clouds and precipitation need moisture in a Coolidge method to form. Typically, we think of lift as causing that, and we showed a variety of mechanisms for that.